Hello students, in this video we'll see how the chain rule can help us find a general solution to the one-dimensional wave equation. Let's consider the one-dimensional wave equation, which is FTT is equal to Fxx, where here f is a function of x and t. In this context, we typically think of t as time and x as space, right? So this is the 1D wave equation. This is the 1D wave equation. Following what we did for the transport equation, we're going to change the coordinates. So here's going to be our coordinate change. We're going to let xc be x plus t, and we're going to let eta be x minus t. We're going to rotate the coordinates. And let's see what happens when we do this. So what will ft be? Ft will be f xc, then partial xc partial t, which would be what? Just going to be a 1. And then we're going to have plus partial f partial eta, and then partial eta partial t, which is going to be a -1. That's partial f partial t. What's partial f partial x by the chain rule? It's partial f partial xc times partial xc partial x, which is equal to 1, plus partial f partial eta, which is, and then partial eta partial x, which is also equal to 1. With the transport equations, we just add these equations together. Now I need to do one more derivative. So what this tells me is that partial f partial t, to do a t derivative, I do an xc derivative of the function, then I subtract off an eta derivative of the function. And to do partial f partial x, what I'm going to do is I'm going to do an xc derivative plus an eta derivative. So now let's iterate this and do two derivatives. So if I want to do the t derivative of the t derivative, that would be the t derivative of the t derivative. How will I do that? Well, I'm going to do an xc derivative of the t derivative, f xc minus f eta, and I'm going to subtract off an eta derivative of the t derivative, which is this. So if we simplify, that's what we get. I'll get an f xc, xc, and then I'll get an f xc eta with a negative sign, and another f xc eta with a negative sign. So it's going to give me two of those. So I'm going to have -2 f xc eta, and then finally I'll have a what? I'll have a negative. Then we'll have a what? Then we'll have a positive f eta. Okay, so I'll have a positive f eta. That's the second t derivative. Let's look at the second x derivative. Fxx will be what? The x derivative of the x derivative. And how do you do an x derivative? You do an xc derivative. So an xc derivative of the x derivative plus an eta derivative of the x derivative. And now let's balance our terms. What are we going to get over here? So what will we get? Let's take a look. So we'll get an fxc. Then we'll get what? Then we'll have 2, so we'll have a +2 fxc eta. And then what? Then we'll have an f eta plus f eta. Okay? Now, we know that FTT has to be equal to Fxx. So these two equations over here have to be equal to each other. And so what does that tell us? Well, clearly those two things are equal. And so what do we have on both sides of the equation? We have an Fxc on both sides of the equation, so that can just cancel out. We have an f eta on both sides of the equation, so that just cancels out. And now I can combine both sides of the equation and conclude from this that 4 Fxc eta is equal to 0. So if I can solve this partial differential equation, I can solve the one-dimensional wave equation in general. Let's think about this. So can we think of a function that when I do an xc derivative, I get 0, then I do an eta derivative, I get 0? Well, the only functions that have this form, this implies that f of xc and eta is equal to some function, I'm going to call it a of xc, plus some function b of eta. Let's check and see if this works. If I do an eta derivative of this thing, this a will go away. Then if I do an xc derivative of the result, that b will go away. That's good. If I do So if I first do an eta derivative, that will eliminate the a of xc. If I then do an xc derivative, that will eliminate whatever's left over with the b of eta. So the general solution has this form over here as a function of xc plus a function of eta. We can think of that by subsequent integration. If I do an eta integral over here, I'm going to get some function of xc. Then if I do an xc integral over here, I'll get some function of eta. So that's how this structure forms. And so what we can see from this is we see, therefore, that in the xt coordinates, our general solution to the one-dimensional wave equation is going to be a function a of xc, and xc is what? X plus t, plus another function, b, of x minus t. So any function of x plus t plus a function of x minus t will solve the wave equation. So for example, you could think of a function like this. You could think of a function e to the x plus y minus the sine of x minus y will be a solution to the wave. If I change t's to y's, that will be a solution to the wave equation. So if I change all those t's to y's. If we look at a function like this, e to the x plus t squared minus the tangent of the square root of x minus t, wherever that's defined. So wherever that's defined will be a solution to the what? That'll be a solution to the one-dimensional wave equation. Thank you very much.